comes out of 8.2, derivatives of exponential functions. In this question we're going to do a curve sketch, and we're asked to sketch this f of x equals e to the negative x squared. Now I don't presume that any of you would know what that looks like off the top of your head, at least I certainly wouldn't if you just gave it to me randomly. So let's go through the curve sketching steps. Our first thing often was domain. Well, there's nothing that x can't be. X can be any real number. There are no vertical asymptotes, there's no non-permissible values, nothing that x is not allowed to be, no square roots of negatives, logs of negatives, etc. The next thing we like to do often is our intercepts. If we try letting y equal 0 and solve for x, the answer is that there is no answer, because you can never have 0 equals e to the negative x squared. There's no exponent in there that'll make that true. Now if we let x equal 0 and solve for y, we're going to have e to the 0, which means we have y equals 1. So if nothing else, on my graph I should have a point at 0, 1. Now the other thing we often do before we get into the derivatives is we look at the symmetry. This thing does have some symmetry to it, because it turns out it doesn't matter whether you put in a positive or negative number for x. This is what we call an even function, where f of negative x is the same thing as f of x. And so we will have symmetry about the y-axis in that way. Asymptotes, I already said there wouldn't be any vertical asymptotes because there aren't any non-permissible values, but if we look at the limit as x approaches either positive or negative infinity for this particular function, if you put in gigantic numbers, whether positive or negative, since we're going to square them, and then you do e to the negative gigantic number, what you will approach is 0. And so y equals 0 is a horizontal asymptote. So I can put in y equals 0 on my graph down here, label y equals 0 as a horizontal asymptote. So I'll have to make sure my picture agrees with that. So now I get to the point where I actually need to start taking derivatives. My first derivative shouldn't be too bad. It's going to be e to the negative x squared times the derivative of negative x squared, which is negative 2x. And so what I'll find is that there is only one critical value, and that is at 0. If I check numbers to the left and to the right, if I put in a number that is negative, I'm going to have a positive times a positive, which means that this thing is increasing everywhere in the interval from negative infinity up to 0. And if I put in a positive number for x, I get a positive times a negative, which means decreasing everywhere from 0 to infinity. So I have a max, not even just a local max, but an absolute max at 0, 1. Now that happens to already be the point that I've got on my graph, so I didn't even find a new point, but still useful to know that that's the highest this graph ever goes. Now my second derivative, I guess, requires a tiny bit more work. I need to do a product rule here, so I'm going to say e to the negative x squared times the derivative of negative 2x, and then plus negative 2x times the derivative of e to the negative x squared, which is this. If I carry out a little bit of factoring of that one, I can see that I've got for sure a negative 2 common to both, and an e to the negative x squared common to both. So the question is, what do I have left? If I take all that out, well, I've got 1, and I've got minus 2x squared. And so that's my second derivative. If you look at that and try to figure out where your critical numbers for that are, so what you find if you solve when does this equal 0, this first piece of it never equals 0, so it's just when does 1 minus 2x squared equal 0, when x squared equals 1 over 2, so when x equals plus or minus the square root of a half. So you do have two numbers to check here, the square root of a half and negative square root of a half. If you check the concavity here, what you'll find is that you have this second derivative is positive, then it's negative, and then it's positive. So you actually do have 2 points of inflection, one at negative square root of a half and one at positive square root of a half. You have concave up everywhere leading up to the first one, so concave up on the intervals from negative infinity to negative square root of a half, and from square root of a half to infinity, and the only place where this thing is concave down is in between, so on the interval from negative square root of a half to positive square root of a half. Now if I want to find the actual points there, I have to put square root of a half into the original function. Doesn't give you a nice answer, but at least the square root goes away. You get e to the negative a half for each of them. So, that's a decimal answer somewhere in here. So you have square root of a half, comma 1 over root e, if you prefer, negative square root of a half, 1 over root e. Again, the symmetry tells me that needs to be on both sides anyway. So we have, this thing should be increasing in concave up all the way to here, then increasing in concave down, then decreasing in concave down, and then decreasing in concave up, and it has to head towards this asymptote. So we have a curve that looks kind of like a hill or something, and so you can do the same things with exponential functions now that you know how to differentiate them that you ever did with trig functions or even just polynomials or anything else from before.